This demo is about the thermodynamics of the reaction between baking soda and vinegar. The purpose: in this demo you will learn how to calculate the heat produced or released by a reaction and use that to predict the delta H, delta S, and delta G of the reaction, which is the enthalpy, entropy, and Gibbs free energy changes. For the demo, you need an insulated cup, 200 milliliters of vinegar, baking soda, a scale, and a measuring cup. To do the demo, measure out 2 grams of baking soda with the scale, place 200 milliliters of vinegar in the insulated cup, observe the temperature of the vinegar using your hand. This is not ideal. Ideally, you'd use a thermometer to measure the temperature, but I didn't have that, so I had to measure the temperature qualitatively. Place the baking soda in the cup and observe the new temperature of the solution. Predict the sign of the change in temperature. Using the change in temperature, predict whether the reaction produced or released heat, and use the heat value to predict the enthalpy change, entropy change, and Gibbs free energy change. I'm pouring 200 milliliters of vinegar into the insulated cup. I don't have a thermometer that can accurately measure it, so I'm going to just dump the baking soda in and see qualitatively if the temperature goes up or down, because the vinegar was at room temperature before. In the reaction between baking soda and vinegar is shown below, and the solution decreased in temperature as the reaction progressed, so the temperature change is negative. And since Q equals mc delta T and the temperature change is negative, the Q value would also be negative. However, what I was measuring was the solution, which is the surroundings. So the Q of the system, the heat produced or released by the system, would actually be positive as the system absorbed heat as the reaction progressed, which made the solution decrease in temperature. So since the system absorbed heat, which means the Q and delta T of the system are positive, the reaction is endothermic. So the enthalpy of the reaction, which is the delta H, is just another measure of the heat energy. It's instead of in joules, it's in kilojoules per mole. So we would find that by dividing the heat by the number of moles used up in the reaction. However, since the reaction, I don't actually have values, but we know that since the reaction is endothermic, the enthalpy change of the reaction is positive, as we are just simply dividing Q by a mole. The sign of the value will not change. And the entropy is a measure of the disorder of the system. There are more moles of gas on the product side of the reaction than the reactant side. Therefore, the entropy change of the reaction would be positive, as when gas is produced, the disorder increases. Then lastly, we have the Gibbs free energy, which tells us whether or not the reaction is thermodynamically favorable and spontaneous. So the reaction occurred without any added energy. Therefore, it was thermodynamically favorable. And also, we could use the equation delta G equals delta H minus T delta S to calculate the Gibbs free energy change. Or we could use RT ln K if we had those values. However, the equation alone wouldn't, and the sign simply wouldn't give us the delta G, because they're both positive, which means that for delta G to be negative, which means it's thermodynamically favorable. If it's negative, all we know is that delta H is positive and that delta S is also positive, so the delta G would be temperature dependent. However, from the reaction, we can see that at room temperature, delta G is negative and the reaction is spontaneous. and thermodynamically favorable.